Okay, we're group A16 of the EECS 203 class in discrete mathematics, and we're going to talk a little bit about logical equivalences and how to prove them using rules. My name is Steve. I'm a group of the A16.
I'm Robbie.
And this is Eric.
And Paul, our off-screen script writer, couldn't be here today. So instead, we have an artist depiction of Paul. That is Paul. Now, moving into the math, we're going to talk a little bit about truth tables. Now, truth tables are a very useful tool to improving simple logical equivalences, and it's kind of the base and the foundation of how we prove logical equivalences. So, to take any proposition, you can take a truth table, and if you prove that the propositions have the same truth table, it's kind of like saying 0.75 equals 3/4. You're saying the same thing just in a different way, and that's you can prove that if it has the same truth table. Now, drawing a truth table is pretty simple. You take each variable and then each proposition that follows from that variable and give it its own column, essentially drawing out all these columns and evaluating their truth values. Now, you have to evaluate each combination of variables when you're doing this. And so, unfortunately, you have to be doing this for a while.
Steve, what are you doing?
Oh, I'm just drawing out this truth table, Robbie. Why? What's up?
Well, there's a better way to do this.
Oh, just give me 1 more hour and I'll have this truth
No,
table all drawn out.
I'll show you.
Oh.
Get out.
All right.
Well, truth tables can show us that that we can prove a statement's correct. It is a long and tedious way to do it, and, well, frankly, there is an easier way. We have a set of logical equivalences that we can use to prove certain statements are true, like the identity laws of P and true and P or false. They're both equal to P, and these are, like I said, the identity laws. We have domination laws, which is P or true is equal to true, and P and false is equal to false. There's idempotent laws, which is P or P is equal to P, and then P and P is equal to P as well. We have a double negation law, which is not P is equal to P. We also have commutative laws, which is P or Q is equal to Q or P, as well as P and Q is equal to Q and P. And the list goes on and on. We also have associative laws. P or Q or R is equal to P or Q or R. And the list goes on. Some important ones that we need to know are the De Morgan laws, which are not P and Q is equal to not P or not Q, and not P or Q is equal to not P and Q. So, with this De Morgan's law, we can prove the statement that Steve was trying to prove in one fell swoop. He was trying to prove that not A and B is equal to not A or not B. And since we have De Morgan's law, we can prove this in one fell swoop since they look almost identical.
Cool. Now, since Robbie had already told you guys all these cool laws and De Morgan's law, now it's time for us to actually apply these laws to real-life problems. I guess we have all seen a lot of problems that have this format: show that blah blah and blah blah are logically equivalent by developing a series of logical equivalences. Now, how to actually do a series of logical equivalences? The best way is actually memorizing everything Robbie just taught you. I hope you guys have listened carefully to what Robbie has to offer before. Too late right now. I'll just run through how to do this problem. So, the problem over here is not P or not P and Q is equivalent to not P and not Q. So, let's think it like easier. Let's just put P is raining and Q is snowing. I hope this is really easy to tell because we have been raining and snowing for the past 2 days. So let's think it this way. First, not raining or not raining and snowing. That itself just sounds a little bit hard to understand. Don't mess around. I'm pretty smart, but this is just pretty hard to understand. Okay, fine. But how does this statement comes to not raining and not snowing? Well, I guess I'll just try Stephen's way of doing a truth table. Let's try a truth table. If I list out P, Q, and then I have to list not P and Q, and then I also have to list out P and not P and Q, and also I have to list PQ for not P, not Q, and not P and not Q. To me, that's a little bit too much. I don't like to write everything 4 times, especially when it's just crazy. I could make mistakes, like I always do. Alright, let's think of an easier way. What's the way to express the logical equivalence statement of this one? First, remember what Robbie just told you? Second, De Morgan's law, which states not P or Q is equivalent to not P and not Q. So let's apply it to our situation. First, this one is a not that we're looking at, and then P or Q. So easily we can tell how it corresponds to the second De Morgan's law. So now we get not P and not Q. Now it comes to this new statement, which is equivalent to the previous one. Now we use the first De Morgan's law. So the first De Morgan's law says not P and Q is equivalent to not P or not Q. Now I'll show you one more time how they correspond to each other. Not P or we might have a technical difficulty over here. So, over here, by first De Morgan's law, it states that not P and Q is equivalent to not P or not Q. Now, how are we going to switch it back to not P and Q? So this is where, sorry, I stumbled a little bit. It's actually really easy to get messed up.
That's the second distributive law, Eric. That's another one of our laws.
Come on, I'm not there yet. Okay, so this is the part I want to use first De Morgan's law. So from here to here, this is how I use De Morgan's law. So I have not P and Q is equivalent to not P or not Q. See, we have not P and P, which is very confusing, but this is how De Morgan's law can be applied. Move on. When we spot like not P, it is pretty intuitive, but now there's a rule called double negative rule, which states not P is P. It's pretty intuitive to me, right? I hope it's also intuitive to you. Okay, so with the small magic of double negative rule, we could switch it to this statement. Now moves on. We use the second distribution law to distribute our P and Q out. Keep going. So we have not P and P, which is false. Now, we use commutative law for disjunction to switch the place of these two statements. Now it comes to the statement of not P and not Q, or false. By identity law, we know that P or false is P. That means P or false is our conclusion P. Now remember, like the beginning of the problem, we want to prove not P and not Q is equivalent to the original statement. So this is our proof. I hope you understand. Thank you.